ECE 307, Basic Electrical Engineering at Clemson University.
Let's just talk about general amplifier to start with. Just the general problem of taking a small signal and turning it into a higher power signal. Here's what a system would look like. You'd have some input, some source. That could be our iPod, where it doesn't have a lot of power. We want to put it into some kind of system that increases the power and then can drive that through a load. So this could be our iPod. This could be the amplifier. This increased power here could drive a speaker system that we could hear in a room full of people. So in this system, for a given Vn, the voltage level, the power, Vn times In, is going to be small. That means the amplifier has to have a large impedance. The Zn equal to Vn over In has to be large. That's a characteristic that we'll be looking for in an amplifier. The amplifier can't consume a lot of the power that this device supplies, because this device can't supply a lot of power. So the voltage and current relationship at the input to the amplifier has to be such that there's a high impedance here. This input circuit sees a high impedance in my amplifier. The amplifier is probably going to increase the voltage level so that the output is equal to some A times the input, and generally that A is going to be greater than or equal to 1. The output is bigger than the input, and so then the power out is going to be bigger than the power in. That's the second characteristic of the amplifier. It's going to make the output bigger in some way than the input. Question then, what circuit components that we have that we could build an amplifier? Here's the first configuration, the inverting amplifier. Here's our op amp, and we connect two resistors and some other connections, and this makes this an inverting amplifier. What we want to do is take this signal right here, increase it, and produce an output. So the gain of our system will be between V out and Vs. RS and RF, that's part of the design of this amplifier. So we'll see how RS and RF affect the gain of the amplifier. So the non-inverting terminal, it just connects to the ground. So you need to identify this whole connection as the inverting amplifier. So we take the output, we have this feedback resistor that comes back to the input, we have this resistor that connects to our input, and then we have this connection to ground. When you see this connection, you have to know that it's an inverting amplifier, because we'll develop equations that describe the input-output relationship. Here's the assumptions we're going to use. The input current is 0, and this input voltage is 0. We're going to use those assumptions about our amplifier to derive the gain between the output and the input. A result of our connection is that this is going to be 0 volts. This is just a short to the ground, the reference node. To set up our analysis, we'll label some node voltages. We'll call this node 1, node 2, node 3. They'll all be referenced to this ground. So for example, V2 is connected from here to here. V1 would connect from here to here. That definition of V1 means it is equal to Vs. And V3 connects from here to here. That definition means V out equals to V3. Again, it's the connection of these resistors and the short to ground that make this the inverting configuration. Here's how we analyze it. I've drawn those assumptions on here again because we're going to need those. We can write a Kerckhoff Current Law at node 2. So right here, we can sum the currents out of that node. We can say that V2 minus V1 over RS, that's that current away, plus V2 minus V3 over RF, plus IN equal to 0. That's the Kerckhoff Current Law right there. We know that V1 is equal to Vs, so we could substitute V1 equals to Vs. V3 equals to V out, we could substitute that. And then our op amp model is that this voltage is equal to 0. We know that V2 is equal to 0 because this voltage and this voltage, they're equal to 0, and V2 is actually equal to the sum of those two, and so V2 is equal to 0. We make those substitutions into this equation, and we can write that in V2 as 0, and V1 is equal to Vs, then V2 is 0 again, and V3 is equal to V out, and you see we can solve V out as a function of the input. This is the relationship we're looking for. We could divide by Vs and talk about gain, but we were looking for an input-output relationship, and you see that the output is a function of that resistor ratio, RF to RS, and it has a minus sign. That's why it's called inverting. The output is the negative of the input. That's why it's called an inverting amplifier. And here's the magnitude of the gain. You can pick RF and RS to create amplification. If RF is twice as big as RS, then the gain is going to be 2. So now, whenever you see this circuit, you can do one of two things. You can reproduce this analysis, which is not terribly complicated, or you can use this equation directly. Anytime you see this inverting configuration, V out is equal to minus RF over RS times Vs. And you can also use it another way, that if I need an amplifier that it's okay to invert the output from the input, I could draw this circuit and know that this gain applies. RF and RS then become design parameters to make an amplifier that has the gain that I seek.